Welcome all. I am Dr. Smriti Dwivedi. In this session, I am going to discuss about the another spectroscopy, which is of Raman spectroscopy. In previous lectures of IR spectroscopy, we found that it is due to the absorption spectra of vibrational and rotational states of diatomic molecules. It means IR spectroscopy is due to the vibrational and rotational states of the diatomic molecules. The origin of IR spectra is due to the changes of dipole moment due to the vibrational and rotational levels motions. In the previous lecture, we studied about the selection rule of IR spectroscopy. In the selection rules, we found that IR spectra is formed when there is change in the dipole moment. However, homonuclear diatomic molecules neither possess permanent dipole moment or nor induced dipole moment due to the vibration. Thus, these levels are inactive or forbidden in case of IR absorption. But the Raman spectroscopy is a tool to overcome this problem. Here we will learn the origin of Raman spectrum and its application, and we studied how we overcome the problem of homonuclear diatomic molecule. The topics we are going to discuss here is theory of Raman spectroscopy, selection rule, Raman instrumentation, what are the difference between the Raman spectroscopy and IR spectroscopy, and lastly we discuss about the application of Raman spectroscopy. First, now come to the introduction part of Raman spectroscopy. The frequency range of Raman is around 4000 to 50 centimeter inverse for both Stokes and anti-Stokes. Raman spectroscopy is generally, it is an inelastic scattering by molecules which was first discovered by Sir C.V. Raman in 1928, and he was awarded Nobel Prize for this fundamental work in 1930. By nature, it is a very weak effect, approximately 1 in 107 photons. It is a type of spectroscopy which deals not with the absorption of electromagnetic radiation, but it deals with the scattering of light by the molecules. Most important point, the phenomena. Earlier in IR, in UV, you studied about the absorption, but in this spectroscopy, it deals with the scattering of light by the molecules. When the substance, which may be in gaseous, liquid or solid, is irradiated with monochromatic light of definite frequency nu, a small fraction of the light is scattered. Now, we will discuss in detail about the theory or the principle of Raman spectroscopy. Let us consider a photon of frequency nu naught falling on a molecule. If the collision is elastic, then the scattered photon will have same energy as the incident photon. But if the collision is inelastic, there are two types of collision. If collision is elastic, then the scattered photon will have same energy as the incident photon, but when the collision is inelastic, the scattered photon will have either higher or lower energy than the incident photon. If we further assume that kinetic energy of the photon and the molecule remain unchanged before and after collision, then from the law of conservation of energy, h nu naught plus E is equal to h nu naught plus E dash, where this is the energy of incident photon and this is the energy of scattered. This is scattering frequency, nu v, it means frequency after scattering of the light. This is the energy of scattered photon after collision, where E is the energy of the molecule before collision and E dash is the molecular energy after collision. Now, we are discussing the quantum theory of Raman effect. Let us consider a system where E naught is the ground electronic state and this is mu double dash is equals to 0, 1 are the vibrational states of the ground electronic state. This is the vibrational states, vibrational energy states. If the light of frequency nu naught incident on the system, three cases may be arrive. Here we will discuss the three cases when photon with frequency nu falls on the molecule. First of all we discuss the first case. In the first case you have seen a molecule with no Raman active modes absorbing a photon with frequency nu naught and return back to the ground state. Return back to the ground state vibrational basic vibrational state after emitting light with the same frequency, and such type of interaction is called Rayleigh. It means if initial frequency is not initial frequency is nu naught, after some time after scattering, when it comes back in the basic vibrational state, its frequency becomes this. It means this is equal to this in case of Rayleigh scattering. Now, it is called Rayleigh scattering, but this is due to the elastic collision scattering takes place. But when inelastic interaction or collision takes place, then there is a creation of Raman lines. This is your Rayleigh and this is the Raman line. Raman line, there is a formation of Stokes and Anti-Stokes. Now, we will discuss the second case of Stokes Raman scattering. In the second case, similarly, let us consider a photon with frequency nu naught is absorbed by the Raman active molecule in its basic vibrational mode and come back to the higher vibrational state. As a result, part of the photon energy transferred to Raman active mode with frequency nu v and the resulting frequency of scattered photon is reduced to this, which is typically referred as the Stokes frequency or Stokes. Let us see. The molecule absorbs the energy and come back by releasing energy into the higher vibrational state, not in the basic state. It will come to the next higher state. If it has frequency nu 0, it is, and after scattering frequency is nu v. So, now initial frequency is more than scattered frequency. Then we got the Stokes line. Now, we are going to discuss the third case, which is of anti-Stokes. In the third case, a photon with frequency nu naught is absorbed by a Raman active molecules, which is already in its excited vibrational state. As a result, excess energy of excited Raman active mode is released, and hence molecules return back to the basic vibrational state, resulting in a frequency of scattered light goes up to nu naught plus nu v, initial frequency and after scattering. This is called anti-Stokes. In this slide, this is the anti-Stokes molecule already in the higher excited state. After absorbing energy, it moves to the virtual energy state, and after that when it come back, it is not coming back to the state that from which it move. It will come to the basic vibrational energy states. So, if this is your initial frequency, incident frequency, and this is after scattering. Now, in this case, initial frequency is less than scattered frequency. So, this is your anti-Stokes. Now, in most of the general cases, main part of the incident light is transmitted without interaction, and which is quite useless for practical purposes of molecular characterization. A part of the incident light may also be absorbed by allowed electronic transition, and which is emitted as fluorescence. In this way, we discuss how there is a formation of Rayleigh and Raman lines. Now, come to the, now it is very important part, only about 10 to the power minus 3% of incident light produces inelastic scattering of Raman signal with frequency, initial frequency plus incident frequency plus minus scattered frequency. Hence, special measures are then done to distinguish the Raman signal from the dominant Rayleigh scattering by adopting various tools such as filters, aperture, double and triple spectrophotometric spectrometric systems. This table summarizes the scattering process which is relevant for Raman spectroscopy. In short, we can summarize, this is Rayleigh, Stokes and anti-Stokes. If scattering is elastic in case of Raman, while it is inelastic in case of Stokes and anti-Stokes, while energy transfer in Rayleigh is none, while in case of Stokes, energy is transferred from photon to molecule, whereas in case of anti-Stokes, energy transfer from molecule to photon. Next is, what is the effect on molecule? There is no effect in case of Rayleigh, but in case of Stokes, excitation of vibration or rotations, while in case of anti-Stokes, de-excitation of pre-excited vibrations or rotation. Next is effect on photon. There is change in the direction of photon, but wavelength remains same, while in case of Stokes, there is change in direction, but wavelengths become higher, while in case of anti-Stokes there is change in direction but wavelength lowers. The probability of occurrence, Rayleigh scattering is very common, Stokes not so common, very rare, while anti-Stokes is extremely rare. This phenomena is very rare. Elastic and inelastic collision between the radiation and interactive molecule results in the formation of Rayleigh and Raman lines. In terms of excitation of electrons, we can easily explain in a simple, if absorbing frequency is equal to exciting frequency or scattered frequency, it is called the Rayleigh line, while if absorbing frequency is greater than exciting frequency, it is called Stokes line, while if absorbing frequency is less than exciting or scattered frequency, it is called the anti-Stokes line. The intensity of Rayleigh line is more than the Stokes line, and the intensity of Stokes line is very much greater than the anti-Stokes line. The anti-Stokes lines are very difficult to observe in conventional Raman spectroscopy because they correspond to the return of molecule from unstable excited vibrational state to the ground state, and initially there are very few molecules in the excited vibrational state. Now, Raman also explained the phenomena of Raman shift. Raman further observed that the difference between the frequency of incident light and that of the particular scattered light was constant depending only upon the nature of the substance being irradiated and was completely independent of the frequency of the incident light. If nu naught is the frequency of incident light and nu that of the particular scattered light, then their difference is called Raman frequency or Raman shift. The difference in the frequency of incident light and in the frequency of scattered light is called the Raman frequency or Raman shift. Therefore, from equation 1 we can write equation 2 like this. We can write equation 2 as E dash minus E is equals to H nu or in incident frequency minus scattered frequency. We can like this, and this is your Raman frequency of wave number in the form of wave number. The shifts in the frequency are called Raman shift. This Raman shift falls in the range of 100 to 4000 centimeter inverse for vibrational energy changes. Their values are smaller for rotational energy changes. Since wave number is equals to 1 by lambda, the wave number in centimeter we can write like this, 10 to the power 8 upon wavelength in Armstrong. This is your Armstrong. Raman shift in per centimeter is given by this equation. This is your wave number of Raman shift in terms of wave number. With the help of this formula, we can able to calculate the Raman shift, where this lambda is excited wavelength corresponding to the exciting or incident frequency. With the help of this formula, we can easily calculate the numerical. In this numerical, a sample was excited by the 4358 Armstrong line of mercury, and the Raman line was observed at 444 7 Armstrong. Calculate the Raman shift in centimeter inverse. You already know the formula of Raman shift. By putting the value of line in the Raman shift equation, you got the result. This is your 4358 is your exciting frequency, and this is your Raman 4447 Armstrong, and the answer is come in this value. Now, the next and the most important thing is the polarizability of molecules and Raman spectra. Polarizability. As you studied in IR spectroscopy, the condition for IR absorption is that there must be a presence of dipole moment, or there is a induced dipole moment must be present in the molecule. Likewise, the condition for Raman spectra absorption is that molecule should possess polarizability. The meaning of polarization is distortion of the electron cloud. Polarization or polarizability is the distortion of the electron cloud. Due to this electron cloud distortion, there is development of the dipole moment in the molecule. A molecule scatters light because it is polarizable. Hence, the Gauss selection rule for a molecule to give rotational Raman spectrum is that the polarizability of the molecule must be anisotropic. Polarizability decreases with increasing electron density, increasing bond length strength, and decreasing bond length. Active Raman vibration. It shows that there must be a change in polarizability of the molecule during vibration. If there is no change in polarizability, it does not show Raman spectra. So, polarizability is the condition of the Raman spectroscopy. On the basis of this, all diatomic molecules like linear molecules and non-spherical molecules give Raman spectra, that is, they are rotationally Raman active. On the other hand, spherically symmetric molecules such as methane, SF6, etc. do not give rotational Raman spectra, that is, they are rotationally Raman inactive. These molecules are also rotationally microwave active. In general, IR tend to emphasize of polar functional group, while Raman emphasizes on aromatic and carbon backbone. Now, come to the selection rule of for Raman spectra of diatomic molecules. The selection rule for vibrational Raman spectra of diatomic molecules is delta mu is equals to plus minus. It is vibrational level, it means it may be plus minus, or it may be plus 1, or it may be minus 1. It may be absorption or it may be emission. But the selection rule for pure rotational Raman spectra for a diatomic molecule is delta J for rotational is equal to 0 plus minus 2. Delta J is equals to 0 corresponds to the Rayleigh scattering, whereas delta J is equals to plus minus 2, it gives rise to the Raman line. The operative part of rotational selection rule is only delta J is equals to plus 2, and it corresponds to the Stokes line. Since delta J is equals to 0, which corresponds to the Rayleigh scattering, and delta J is equals to minus 2, it is correspond to the anti-Stokes, and it must be ignored. It means rotational level 0 and -2 must be ignored, as the rotational quantum number of the upper state must be greater than that of the lower state. So, the operative part is only delta J is equals to +2 for rotational, and for vibrational it is +1 -1. Now, come to the advantages of Raman spectroscopy over the IR spectroscopy. Raman spectroscopy are independent of the frequency of the incident radiation, and hence most important part, and hence by suitable adjusting the frequency of the incident radiation, Raman spectra can be obtained in visible spectrum. Raman spectra can be obtained even for molecule O2, N2 and C2 etc., which have no permanent dipole moment, and such a study has been not possible by IR spectroscopy. Raman spectra can be obtained not only for gases but even for liquids and solids, whereas in IR spectra for liquid and solids are quite diffuse. We can get the spectra, but it is very quite diffuse. Now, come to the Raman instrumentation. The modern Raman spectroscopy consists of 3 components: laser source, sample illumination system and suitable spectrometer. The source used is always nearly a laser. Because of the high intensity is necessary to produce Raman scattering of sufficient intensity to be measured with a reasonable S/N ratio. S/N means signal to noise ratio. Better the signal noise ratio, better is the quality of the spectra. The next part we have to know about it, which wavelength is suited. We have discussed about the best suited laser wavelength. The correct selection of the laser wavelength is very important part for Raman spectroscopy, because in modern equipment several laser wavelengths can be employed to achieve the best result of the Raman signal. For example, many samples, especially those of organic or biological nature, will be quite fluorescent species. Exciting these samples with a laser in the range of green 532 nanometer may promote this fluorescence and may swamp any underlying Raman spectra to such an extent that it is no longer detectable. In this instance, the use of laser in the range of red 633 nanometer or near infrared 785 nanometer may provide a solution. With the lower photon energy, a red or near infrared laser may not promote the electronic transition and hence fluorescence. So, the Raman spectra may be far easier to detect. Argon and krypton ion are the sources that emit the blue and green region of the spectrum, have an advantage over the other source. Some common laser sources of Raman spectroscopy is argon ion, krypton ion, helium and diode etc. Sample illumination system, how sample can be illuminated in the Raman spectroscopy, because sample handling of Raman spectroscopy is another important part. We can't use in this sampling handling for Raman spectroscopy measurement is much simpler than IR spectroscopy, because glass can be used for windows, lenses and other optical components. In addition, the laser source is easily focused on a small sample area and the emitted radiation efficiently focused on a slit. Consequently, very small samples can be investigated. A common sampler holder for non-absorbing liquid samples is ordinary glass melting point capillary. Ordinary glass melting point capillary. If the sample is colorless, it does not absorb a visible laser, but if the compound is colored, it can absorb the laser and get hot and decompose. Sample illumination can be done by reduce the laser power or change the wavelength, dilute the sample with KBR pellets, further cool the sample, rotate or oscillate the laser beam on a sample. Liquid samples. A major advantage of sample handling in Raman spectroscopy compared with IR is because water is a weak Raman scatterer but a strong absorber of IR radiation. Thus, aqueous solution can be studied. Most important point, aqueous solution can be studied by Raman spectroscopy but not by IR spectroscopy, and this is the advantage and is important particularly for biological and inorganic systems in studies and dealing with the water pollution. Solid samples are acquired by filling a small cavity with the sample after it has been ground to a fine powder. Polymers can usually be examined directly with no sample pre-treatment. This is your Raman spectrophotometer. This is the objective lens, this is sample, this is mirror, grating, amplifier, software. This is for inelastic scattered light, this is for the elastic scattered light. Raman spectrophotometer, in this the sample is illuminated with a light beam in the UV visible or near IR range or near infrared range. The scattered light is then collected by a lens or mirror and it is sent through the spectrophotometer to obtain the spectra. Here you have seen, as we know, in this important point is this, spontaneous Raman scattering is very weak due to the intense Rayleigh scattering. Raman scattering is very weak due to the presence of intense Rayleigh scattering. So, suitable filters are placed to remove the major components of elastic scattered light. Elastic scattered light means Rayleigh scattering. This is your filter. With the help of this notch filter, we cut off the elastic scattered light so that only inelastic scattered light pass through the lens. For this, the commercially available notch filters used, which cut off spectral range of 80 plus minus 80 to 120 centimeter inverse. Now, after instrumentation, come to the application part of Raman spectroscopy. Raman spectroscopy is an important tool for study of inorganic species because it is superior to the IR spectroscopy for investigating inorganic system because aqueous solution can be used in case of Raman spectroscopy while it was not used in the case of IR spectroscopy. In addition, the vibration energies of metal ligand bonds are generally in the range of 100 to 700 centimeter inverse. It is a region of IR that is experimentally difficult to study. These vibrations are frequently Raman active. Raman spectroscopy or studies are useful for determining the composition, structure and stability of the coordination compounds. Raman studies have been used in determining the probable structure of many species, like for example, in perchloric acid solution, vanadium 4 appears to be present as vanadial rather than as hydroxide form. Studies of boric acid solution show that the anion formed by acid dissociation is tetrahedral form rather than in this form. Dissociation constant of strong acids such as sulfuric acid, nitric acid, selenic acid, oxopyridic acid have been calculated from Raman instrument. In spite of this, there is many biological application of Raman spectroscopy because of the small sample requirement and minimal sensitivity towards the interference by water. Quantitative application, Raman spectra tends to have less cluttered with peaks than the IR spectra, as a consequence of which peak overlap mixture is less likely and quantitative measurements are simpler. In addition, Raman sampling devices is not subject to attack by moisture. It is a main advantage, and a small amount of water do not interfere. Some disadvantages are also there. Despite these advantages, Raman spectroscopy has not been widely used for the quantitative analysis, and this is due to the high cost of Raman spectrophotometers relative to that of the absorption instrumentation. This is the comparison of Raman and IR spectra. In this spectra you have seen blue line for the Raman less cluttered peak, while this is of the IR peak. Raman versus IR. There is a difference between the Raman and IR. Raman spectra are similar to the IR because they are useful for the functional group detection and the fingerprint region that permits the identification of specific compounds. Raman spectra yields important information about certain types of organic compounds than the IR counterparts. First of all, water is very weak Raman scatterer. Thus, aqueous solution can be easily identified with the help of Raman spectra, while it is not identified with the IR because IR is strong water absorber. Sample container in Raman technique is made of glass, while it is impossible in IR because glass absorbs IR radiation. Raman experiment uses a laser beam of very small diameter around 1 to 2 millimeter, and thus a very small quantity of sample is needed for characterization. The laser source used by Raman needs to be carefully dealt. It would cause local heating for the sample, it may burn the sample or cause to decompose. Raman technique is superior to IR spectroscopy for investigating inorganic system because aqueous solution can be employed. Raman studies are potentially useful source of information considering the composition, structure and stability of coordination compounds. The peaks obtained in the Raman is less cluttered than the IR spectrum, as a consequence of which peak overlapping in the mixture is very less. But Raman spectroscopy has not exploited widely for quantitative analysis because of the high cost of Raman spectrophotometer. Now, we summarize the lecture we studied so far. The main point is Raman spectra arises due to the scattering of light by absorbing molecule. Raman spectra can be obtained for molecules such as O2, N2 and C2 which have no permanent dipole moment, and such studies has not been possible with the help of IR spectroscopy. Raman spectroscopy is usually non-destructive and non-invasive technique, and measured sample can be reused for other purposes afterwards. It is actually a very quick process and takes a few minutes and we get the result. This technique is suitable for aqueous solution, and Raman spectroscopy does not suffer from strong absorbance of water, which is common problem for IR spectroscopy. These are some assignments. Try with yourself on the basis of the lecture I have given. If you have any queries or doubts about the Raman spectroscopy, please you can contact me at my mail ID. You are free to contact. Thank you.